Nati played a very important role in bringing me here to the Institute. And yeah, but I'd like to correct one thing about this story. The story I heard about the bug was slightly different. So, so in the version I heard, there was a bug, and Nati goes, crashes the bug, and then asks any questions. But,
this one I think actually Guess what actually happened? You need a microphone. How many different versions of this story can we hear about? And regardless of what happened, I think it's completely obvious that we cannot have all these versions.
But all these versions are morally correct, right? Okay, so Nati and I collaborated on 8 papers. 5 of them were on aspects of two-dimensional string theory and the relation to matrix models, and this talk is vaguely related to that topic. But I'd like to talk about one important paper of Nati that had a big influence on my research, and it's this paper. So I guess it's 93 according to the citation index of spires. So they do some instanton computation in this theory. This paper contains a phrase that is a favorite of Nati's papers. You'll find this phrase where he completely understands the problem, and it's all determined by the symmetries of the problem. So that paper was from 97, and since 95 to 97, Andy Strominger was always emphasizing to me that the near horizon geometry of D3 branes has maximal supersymmetry. He thought this was an important fact, and that's double the expected number. And certainly I didn't know what to make of this. But this paper contained some calculation of instanton effects, and he did it for 3-dimensional Young Mills, super Young Mills, and 4-dimensional maximal super Young Mills. And they noted that there were, instead of 8 fermion sphere modes, there are 16 because there are extra 16 super conformal symmetries. And that got me thinking that these extra supersymmetries were the same that Andy was talking about, and that the important point was there was a conformal symmetry, so that had to do with the isometries of the near horizon region. And well, that was one of the things that led to AdS-CFT. Now, so that was that paper. So now back to the talk. So we're going to talk about the SYK model, AdS2 and conformal symmetries. A lot of what I'm going to say is related to, well, it's based on the talks that were given by Kitaev, and also, well, we are going to discuss some aspects of work we did with Douglas Stanford and Shenbin Yang. Okay, so there are many models of holography, and so typically we want to relate a large N quantum system to some gravity or string dual. And there are various large N systems that one could consider. The most trivial large N system might be just N free fields. And then there are some more complicated ones. So we can have ON interacting theories. We can have maximally supersymmetric super Young Mills at very strong coupling. And as you go down here, it gets harder to solve them. And many of them are in some sense solvable. So here they can be solved by large N methods. These ones can be solved by integrability. And the Sarche-Kitaev model lies somehow in between. So it's a little more complicated than ON theories, but it's somehow closely related to the ON class. And it's also, in some sense, solvable. And of course, in the gravity and string duals, so the simplest, the easier to solve would be a theory that has Einstein, just purely Einstein gravity, where the higher spin particles are very massive. So it's useful to think about the anomalous dimension of higher spin operators. So it's 0 for free theories, it's order 1 over n for the typical ON interacting theories. In this model, there will be of order 1. And well, of course, in these examples that lead to Einstein gravity, they are much bigger than 1. And so, so these are slightly more complicated sort of gravity systems that we could have in the right-hand side. So this model is also somewhat like the Owen theories, that in addition to the singlet fields, they contain also somehow non-singlet fields, or n fields would contain naively n fields in the bulk. So let me remind you of some solvable Larsen models, and just to put this model in context with other solvable Larsen models you would have encountered. So a simple class of solvable models is based on these rainbow diagrams. Now, the reason why you might have only these rainbow diagrams could be varied, but one simple example, for example, is 2D QCD, where you have a fundamental, and then this is a double line gluon. And there is some gauge choice where you can ignore the gluon self-interactions. And something similar happens in large Chern-Simons theories with fundamental matter in 2+1 dimensions, where you can neglect those self-interactions. And then you get a structure of diagrams which essentially looks like this. So there are propagators that do not get corrections, and then we correct the propagator of the fermions. And this can be summed. So it can be summed in the following way. So first, you have the full propagator is equal to the sum of the 1pi propagators. That's this usual equation. That's a true equation in any theory. In any theory. And the simplification arises when you take this self-energy and you realize that, well, it's given by that propagator, and then you put in again the full propagator, the complete propagator, and that can be expressed in terms of equations as saying that the self-energy is equal to that propagator times the propagator of that red field, which remains uncorrected, times the full corrected propagator of the blue field. Okay, and so this equation is simpler in Fourier space, and this equation is a little simpler in position space or time. If there is only time, it's just position. Yeah, well, let's say position space. Okay, so one special case of this model would be to say that this propagator is just constant. So this was considered in the past by Izuka, Polchinski, and also a paper also with Okuda. And this type of propagator you would get is similar to what, so they considered it by considering, I think, a slow-moving oscillator, but you get something similar if you had a model where you had n Majorana fermions and a Hamiltonian, which contains random couplings by linear couplings of these fermions, where the couplings obey a Gaussian distribution with some width j. And then in this case, you can think of these random couplings. To lead in order in n, you can treat this disordered system as a system that has a very slow, let's say, moving field, where the two-point function is time independent and equal to this Gaussian. And so you treat this additional field. So that's is exactly the same as the structure that you had in the previous model, and exactly the same as the diagrammatic structure we are familiar with those rainbow diagrams. So you can sum those diagrams, and it's simple to sum these diagrams. Now, I'm not going to sum the diagrams for you, but I'm just going to give you a quicker way to see what the solution of this model is, and which is a quicker way which is available for this model, but not for the more complicated models we'll discuss later. So we have this random matrix, and you know how to diagonalize a random matrix. So we'll diagonalize a random matrix. You get a series of eigenvalues that will have some distribution given by the usual semicircle law. And then for each eigenvalues is an antisymmetric matrix. So that eigenvalue will pair two fermions, and these two Majorana fermions just form a single two-level system. And so you'll have two levels with some energy given by the eigenvalue. So here the horizontal direction is the eigenvalue, and here it says how many eigenvalues you have with that particular energy. At low energies, we are going to be interested in these two-level systems that have small eigenvalues. So they are around here. And around there, the number of eigenvalues for given energy is roughly constant as a function of energy. And that's constant distribution is exactly what you would have if you had a massless fermion on a circle of, let's say, size n. So you have very dense spectrum, but as a function of the energy or the momentum, you have a constant distribution. So this is an example where this model started out being some random, with this random Hamiltonian. At low energies, you have this approximate scale invariance, which is the scale invariance of just this massless fermion on this very big circle. Now, this model is too simple because there is no chaos and no black hole behavior, so it's in some sense integrable, because after doing after you go to the eigenvalue basis, you have all these commuting charges, which are all the fermion number operators for each of these two-level systems. Very good. So that's that model. So now we go to the SYK model. So this is a model that was a more complicated version of this model was originally studied by Sachdev and Yi, and then further solved in the way that I'm going to describe by Georges and Percolet. And then Kitaev simplified it a bit by proposing this particular Hamiltonian, particular form of the model, and he also computed 4-point functions and realized some of the pattern of symmetry breaking that we'll discuss later. So the model is very similar to what we had before, except that instead of having 2 fermions, we have 4 fermions. Okay? So now it's a little more complicated because we can't just simply do a rotation. So this is a more interacting model. It's not integrable. And so we have the random couplings again with the Gaussian distribution as we had before. And to leading orders in n, we can treat this J as an additional field. So a correct way to treat this order, as Offer reviewed, was to do the replica trick and so on. But for these models, to lead in order in n, to lead in order in n to the q, to the order we will work at, the results you get by doing the replica trick are exactly the same as the results you would get by treating this J as an additional field whose 2-point function is time independent and equal to this, this value. So J is a dimension-full coupling, and we'll have the model will have in the ultraviolet, it is just free, so it's topological, there is nothing. And then as you go to the infrared, these interactions become important, and we're going to be interested in this infrared vision, where the coupling effectively gets strong. So effective value of the coupling, so since it's dimension-full, so it has dimensions of energy, so the Majorana fermions are dimensionless, there is no number here. And so we have to supply some time, some units of time, could be the inverse temperature. So an effective coupling could be beta times J, or for example, if we are looking at the correlator at 2 different times, it could be that time difference times J. So that effective coupling, we're going to take it in the low energy region, where it's much bigger than 1. But we are not going to take it much bigger than n. So we are, it stays of order 1 in the large n limit. One could consider the other regime, and there are some papers exploring some aspects of the other regime, but we'll concentrate on this one. So the spectrum, of course, is statistically symmetric around the origin because it has equal probability of being positive. These J's can be positive or negative. Now, I want to draw the attention to the fact that the dimension of the Hilbert space is, of course, exponentially large in n. And this Hamiltonian though it has some randomness, it's not as generic as a random matrix. So number of couplings is smaller. It's of order n to the 4th as opposed to 2 to the n. And this low energy region, we concentrate really at the edge of the spectrum, but it's an edge that includes still an exponentially large amount of eigenvalues. Okay? So we're not noticing the discreteness. When we talk about low temperatures, we are not going to go to the single, the last true ground state of the system. We're always going to be considering a large number of eigenvalues. Okay, so let's go back to the diagrammatics and try to understand what makes this model solvable. So before, these are the diagrams we had before. And now we have essentially the same structure, except that, so the red lines denote the propagators of the J field, which, as we said, are constant. And the blue lines are the propagators of the Majorana fermions. And since there were quartic interactions, so when a Majorana fermion comes, it would split to 3, and then it joins again, and so on. And to lead in order in n, for reasons similar to the ones you had in 2D QCD or other systems, or the Chern-Simons theories, you don't want these propagators to cross. So you have this type of structure. And you can, again, have sub-diagrams where you insert the previous structures. And these then have a very similar, the equations have a very similar form compared to the ones that I showed you before. The only difference is that there is a 3 here. Before there was a 1, and now there is a 3. Okay? That's the only difference. And in fact, you can generalize these models. So you can just make this, you can study these equations as a function of q, where this is some number that can be varied. And for integer q, you can think integer even q, you can think of these equations as coming from a model, similar model where you have q fermions. But regardless of whether they come from this Hamiltonian or not, you can just think of about these equations and vary q continuously. Okay. So then q equal to 2 is the case we had before, which we can solve analytically, explicitly, everything. And q equal to infinity, we can also solve analytically these equations by making a certain specific ansatz. I'm not going to describe it in detail. And q equal to 4 is somewhere in between, and you can this can be solved numerically. So you have to what you have to do is do a Fourier transform between position and momentum space, and then solve these equations. And the solution sort of lies in between what you have for these two regimes. Now, a feature of these equations, which you can see analytically very easily, is the fact that if you go to the infrared, then you can assume that the free propagator will be subdominant, and then make an ansatz for the propagator, which is scale invariant ansatz. And then from here, this equation, you calculate sigma. Then you do the Fourier transform of both this and sigma, which is very simple to do. And then you check that this equation is obeyed, and it will be obeyed if delta is equal to 1 over q. So in this case, 1/4. Okay? And you can also then later make the consistency check that for this value of delta, this is indeed subdominant at low energies. Now, not only this, but if G is a solution, and we are given an arbitrary function f of tau, then we can generate another solution which has this form. So we get, for example, we already checked that this is a solution, and then we construct a new solution here using this formula. I didn't write it, which is just simply replacing, doing a reparametrization. This is just the standard formula for a reparametrization of this solution. And so this is going to be a different solution in the sense that it's a different function of tau and tau prime, but it will also be a solution of the equations where we neglect this term. If we include this term, then this is not a solution, but if we neglect it, then it is a solution. So for example, this is useful if we want to go from the 0 temperature to finite temperature solution. We can do this reparametrization and go to a finite temperature solution. So it's also useful for this. Now I'm going to just give you here some form of the propagator, so what the solution looks like for different values of the coupling. So here, if the temperature is very high, so then you you get this when the interactions are very small. You get this when you turn on the so maybe I should explain what is this. So this is saying that the Hamiltonian is 0, so the 2-point function of these fermions is just constant, is time independent. Okay. Then you turn the coupling on, we'll get something non-constant, and when you make it very large, you get some function which can be approximated by this conformal invariant solution that we had here expressed at finite temperatures. And that conformal invariant solution agrees everywhere except at very short time differences. So when the time difference is very small, then we go back to somehow the UV-like behavior, where you get something constant, and you have some small deviation, but only at very short distances, short times. So here there's only time, there is no distance. Sorry, I sometimes say distance because we are thinking about this in Euclidean space, so, but it's Euclidean time. Now, something that is useful for thinking about this model is to think about the large N effective action. This is a common thing to do when dealing with ON models, and it can be also done in this case. So we integrate out the fermions and the couplings to obtain an effective action for the singlet, somehow the fermion two-point function. So on shell, on the equations of motion, G will be the two-point function of the fermions. So roughly speaking, by integrating the fermions, we get this determinant where sigma will then sigma again on shell will have the interpretation of the self-energy, but we get this action. This has a few features. So first of all, if you calculate the equations of motion of this action, you find the equations that we discussed before. Also, it has a factor of n, so it's a classical action. And if we take this and you insert in this action, so you neglect this and you insert the conformal answer, you get the extremal entropy, so that the entropy at zero temperature. It is non-local, so non-local in time, depends on these two times, but seems some of the terms are bilocal. So this function is a function of two times, and if you think of the difference of times as an extra dimension, these terms are local, but these terms are still non-local in that bigger space. Now it's tempting to think that that difference of times is the radial direction, so indeed, and this action is analogous to the bulk action. Indeed, it's in naively two dimensions. But these determinant terms are certainly non-local, and it's also the wrong space. So this is the space of two times is not the same as the space of the bulk. It's sometimes people call this kinematic space, but so it's also in ordinary AdS-CFT, you could think of the space of two times on the boundary, and that's the space of geodesics, for example, between two boundary points. But that's not equal to the bulk space in ordinary holography. Very good. Now, this action has some zero modes, and so which are the ones that we discussed. So we said that if this was a solution, then these were also solutions. And also these solutions have the same action at low energies. And so we have some Goldstone bosons. So we have no action for F, so F is parametrized in these Goldstone bosons. And we would get a divergence in the path integral if we integrate over F, both from the fact that F has a non-compact target and from the fact that you have some infinite number of Fourier modes in F. And the solution to this problem is to remember that the symmetry is also slightly broken. And these deviations from the conformal solution, this breaking, is happening at short distances. Remember when we looked at the expression for the propagator, it's only at short distances that we had some deviations from the conformal answer. So what that means is that we expect to find an effective action for F that will be local in time. So if we insert this into the full action, we expect that the leading correction will not be a bilocal or non-local action in F, but will be an action which will be local in F. So now we don't have a lot of experience classifying non-local actions, or even, but we do have some experience classifying local actions. Right? And furthermore, there are some particular changes of F that leave this G of F invariant, and those are these SL2 changes. And this comes from the fact that this original expression is SL2 invariant. So if we change F in this way, we just get exactly the same G. So those are not doing anything. They are not changing anything, and those should have exactly zero action. So two Fs that differ by an SL2R transformation should have some exactly the same action, not because of any symmetry, but the way we define what G of F is. which is just simply by taking a reparametrization of this conformal invariant solution. So another way to state this is to say that the Goldstone bosons are really the reparametrizations modeled out by SL2. So they live in the coset. Now, the simplest action with these properties, so it's supposed to be an action that is just an integral over time of something that is SL2R invariant. And the simplest one, the one with lowest number of derivatives, is the Schwarzian action, the Schwarzian expression. It should have a factor of n because the action we started with had a factor of n. So this is an approximation to that action involving sigma and g. By dimensional analysis, we see that this action contains two derivatives, so it's perhaps easier to see from this term. So we integrate one, and so we have some, in order for dimensional analysis, we need just one factor of j. And then there is a numerical coefficient that we can't compute just from symmetry reasons. And this numerical coefficient requires knowing the first deviation of the propagator from the infrared solution and can be computed numerically. Now, Nati told me not to consider theories with ghosts. And he really dislikes ghosts. And here, this action is a higher derivative action, which typically will contain ghosts, does contain ghosts. So why is this happening? Here, we should remember that this SL2 symmetry, we should view it as a kind of gauge symmetry, not gauge symmetry in the sense that it's a local symmetry in time, but gauge symmetry in the sense that we should quotient by this symmetry and consider only the physical state. Physical states are states that will be SL2 invariant, and that removes the ghost of this higher derivative action. Okay? And this is the same remark we said before, that the Goldstones are this coset of reparametrizations divided by this SL2. This is a global SL2 gauge symmetry. So at low energies, we started with this effective action that included an integral over all possible g's and sigmas. And the idea is that we can split it into a piece that involves the non-zero modes and a piece that involves those zero modes that we discussed. And in fact, the integration measure can be fixed by also the SL2 symmetry, as was done in this paper. Now, an example of how you can use this is the following. So if you look at the 4-point function, so here we consider the 4-point function. Here we let's say sum over these indices and sum over these other two indices. So that can be expressed as an integral as a function. Well, we had the same functional integral we had before, but now we put two factors of g. And the leading order answer is, of course, the disconnected. Just put the classical expression for g, the classical solution. So that's trivial. But then if you want to consider the first 1/n correction, you would expand the action to quadratic order, and you just invert that quadratic order action. So it's somehow the propagator for g that we're computing when we compute the 1/n correction. Okay? So in a generic large n theory, since there was a factor of n here, you expect that this is 1/n times that inverse of that propagator. But since the leading conformal answer had zero modes, this action, this piece, there will be a piece here that will be enhanced, so the piece that contains the zero modes, and these enhanced terms can be computed using this Schwarzian action. So in other words, you can consider just not generic g's, but the g's that come from integrating only over the Goldstone bosons, and with only this Schwarzian action we had before, and that will give some function of the times, but there will be this enhancement factor of beta j. Remember that we are at large beta j. Okay? So the naive conformal answer would have been independent, so it's independent of beta j, but here we get this enhancement factor due to these slightly suppressed modes. So and here, when we say this thing was just simply the reparametrization of the simple solution, so that's simply this expression. And this gives some explicit function. It's not too complicated, but you can compute it to this order. Involves cosines and sines and so on. So that's so the 4-point function. Then, well, this gives well, this is the same as what we said before. So there is the disconnected part of the 2-point function, and then there is a 1/n correction, which has this enhancement factor. And then there might be other terms I'll discuss later that are not enhanced by this factor. Now, we can use this to compute the Lorentzian 4-point function by analytic continuation, and different analytic continuations give different orderings in the Lorentzian signature. And of particular interest, it is to compute the out-of-time order correlator that is responsible for the growth of commutators. So in this case, the anti-commutators of this size. And when that out of order, so this is an out of order correlation function where we have psi of t and then of 0 and then of t and then of 0. And then we find just from this function that at large times it grows exponentially with a growth that saturates the chaos bound. So there is a bound you can argue based on general principles of quantum mechanics plus some reasonable assumptions about the Larsen nature of the system that bounds this growth to be less than 2 pi over beta. And this has a maximal growth, and so this was computed by Kitaev, and this sparked the interest in, well, at least our interest in this model, because we thought that this was a signature of having a local bulk dual. This I think was incorrect. And this growth is just related to the way that these low energy symmetries are realized in this model. And that's, so here, this discussion in terms of the Schwarzian action shows this manifestly that is due to this property. And the full 4-point function can be also computed. So this is the piece we discussed. And there is also a conformal invariant piece that you can compute by using some methods, some in some ladder diagrams. I will not discuss it in detail. But if you compute this other part, then it contains some information about the operator spectrum of this theory. And you can get the anomalous dimensions of the higher spin field. So here, spin is difficult to define in 2 dimensions. But we are going to define the spin in terms of the number of derivatives that we have for the fields. So in higher dimensions, this would be honest spin. So in 2 dimensions, well, in this case, that there is only one time, this is analogous to spin. And what one finds an equation. Here I wrote down the equation. Maybe I shouldn't scare you, but simple equation in terms of gamma functions that determines these h's. And you find that, well, this is the naive dimension you would expect if there were no interactions between these fermions that have dimension delta. So 2 delta plus odd number of derivatives. And then these numbers are corrections of order 1 that go to 0 for very large m. And they all come from just solving these equations with the function. Now, I like to contrast the way that the SL2 the symmetries are realized in this model as compared to other models that people that have been discussed that have so-called conformal symmetry. So one simple model are this the Alfaro-Fubini-Furlan models where you take a quantum mechanics with SL2 symmetry. So these are models which have an exact SL2 symmetry acting on the dynamical variables. And they don't have an SL2 invariant ground state. And under a general reparametrization, which is not SL2, the action really changes. So in this particular case, it changes by this, well, by the Schwarzian times something that involves a field, the field value. So these actions, these Hamiltonians, are not SL2 invariant in any sense. So, sorry, they are not. They are SL2 invariant. I misspoke. They are not reparametrization invariant. So we don't have any kind of reparametrization symmetry in these models. So they have a really different pattern of symmetry realizations. So they don't have this emergent reparametrization symmetry. that is spontaneously broken and explicitly broken as we have in the SYK model. So these models, these things are perfectly good for describing brane probes in AdS2, but they don't seem to capture the gravitational features of AdS2 quite properly. And now it might be that some more complicated versions of these models works, but at least the simplest certainly the simplest versions don't work. So SYK and AdS2 both have an emergent, spontaneously broken, and explicitly broken reparametrization symmetry. And this, both the spontaneous breaking and the explicit breaking, both preserve an SL2 gauge-like symmetry. Now, there are many questions that one can ask. So this discussion was mostly through the Euclidean path integral. And one would like to understand better how the symmetries are realized in Hilbert space. So the first reaction of anyone coming from the string community is to see this reparametrization symmetry and want to find that Virasoro algebra. And that was my first reaction. I'm sure that's your first reaction. And but we haven't answered this question. So you can see the symmetry clearly acting. So you can see the symmetry in Euclidean space, but I don't know how to think about this properly in Hilbert space. I mean, of course, it has to be an approximate symmetry. The Hilbert space has finite dimensions, so you're not going to find an exact Virasoro algebra, but it would be nice to understand it better. Also, one would like to understand whether there is any central charge that can be computed. Again, okay, so those are questions we don't understand. And don't get your hopes up, the talk is not yet over. So we now, I'd like to also make a connection to something else. So this discussion of reparametrizations, you can also do it in CFT2. So here we were discussing something that looks like conformal theory in 1 dimension, but also in 2 dimensions you have a similar feature. So in 2-dimensional CFTs, of course, we have these holomorphic reparametrizations. And they are spontaneously broken by the vacuum to just SL2 squared. And the Goldstone bosons are just the modes that are created by the stress tensor operator. And the difference with the previous action, with the previous story, is that here they have a non-zero action, which is consistent with conformal symmetry. So this whole structure is perfectly consistent with conformal symmetry. So the symmetry is not explicitly broken, or you can consider systems where it is not explicitly broken, and that's a perfectly consistent theory. Of course, the symmetry algebra is deformed by the central charge and so on, and if in order to view it as an algebra, you want to view this as having some expectation value of C, well, that's the usual story. And another difference is that in the previous discussion, these reparametrization modes were dominant. So even though we had higher spin fields, these reparametrization modes were still dominant. Okay. Here, these stress tensor modes are only dominant in the case that all other operators have very high dimension. But in generic theories, they are not particularly dominant. So that's another difference. Okay, so now I'd like to talk a little bit about near extremal black holes. So of course, when you have a black hole, it's dual to some system with a finite number of degrees of freedom. And extremal ones have an AdS2 near horizon region, and so they should be dual to some conformal quantum mechanics. But conformal quantum mechanics is inconsistent with a finite number of states. I have to speed up slightly. But also, purely AdS2 gravity is not consistent, so that's at least the two sides of the duality work because they are both inconsistent. So what is really consistent is nearly AdS2. So you take AdS2 and the leading perturbation away from AdS2. So you take the area, which is not just the extremal value of the area, but also you consider the possibility of that area deviating slightly from the extremal value. And this leads to, so of course, the extremal area that determines the ground state entropy. And this comes from, let's say, the variations of the area in the additional dimensions, if we're getting this for higher dimensions. But the leading deviation is always described by this very simple so-called dilaton gravity action that was previously considered by these authors. Now here you take this action. The equation of motion for phi implies that the metric is AdS2, and the equation of motion for the metric determines phi almost completely. So that's the AdS2 metric, and then phi is completely determined. The only undetermined thing is the value at the horizon, let's say, and exactly the position of the horizon within AdS2. Now in the full theory, so notice phi is increasing. So in the full theory, for a large value of phi, we'll change to a new UV theory. Okay, so this is only describing some region. So you can take these asymptotic boundary conditions for a problem like this. You fix the boundary condition, you fix the metric along the boundary, and you fix also the value of phi along the boundary. So this is some specific function of the boundary time. You could just take it constant, for example. Now, if you only fix the metric, then there is an infinite number of ways to draw a line of a given length inside AdS2. So there are many solutions. And these many solutions are all related by these reparametrizations we were talking about. So that's the gravity realization of those Goldstone bosons. And once you impose the boundary condition for phi, then there will be a unique solution. If phi is constant, for example, that solution will be a circle. And one can, so that's the case when we think about imposing the solutions. One can get this Schwarzian action in a simple way by starting with the original action, which is this. We've included the extrinsic curvature term at the boundary. First imposing the equations of motion for phi, and then we get the AdS2 metric. And then we evaluate this term of the extrinsic curvature on the curves we saw a couple of transparencies ago, so those curves. And you find, again, the Schwarzian action. So this is an alternative way for fixing the shape of the curve. So one way was to fix the boundary condition for the dilaton. The second is to evaluate this and then find the Schwarzian action, and then solve the equations of motion for this Schwarzian action, and that fixes the curve again. So here T is the usual AdS2 time coordinate, and U is the boundary system or quantum mechanical time coordinate. Right? So somehow the dynamical variable is the change of variables between these two coordinates. You can think of, so also in the previous discussion of the SYK model, you can think of this internal time as determined by the correlations of the system. So remember, it was what appeared in the two-point function. So you can say that the correlations or entanglement determine the flow of that time variable. And then there is this possibility of that time variable differing from the actual time variable of the boundary system. Now there are some qualitative relations. So between this two-point function that we had in the SYK model is analogous to the background AdS2 metric. So it's something SL2 invariant. Both are SL2 invariant. Then we can have non-zero mode perturbations of G. Those are analogous to fields propagating on AdS2. Then there is the discussion of the nearly zero modes of this action, and also this boundary modes of the AdS2. So this is a precise relation. This is not a qualitative relation. So these two things are governed by the same symmetries and are identical. Then we had that so we had some action for these bilocal fields, and those are analogous to an action which includes the dilaton gravity, which is analogous to the Schwarzian action, plus some matter fields. Now, also the fact that there are some correlations. So this conformal answer, if you have finite temperature, you have the thermofield double, and you can have correlations between the two sides. That seems to be related to somehow the fact that the gravity is connected between the two sides. So there are several properties fixed by the Schwarzian, so that are common to both this nearly AdS2 gravity and nearly CFT1, any nearly CFT1 where the symmetry is realized as in the SYK model. And so one is the temperature dependence of the free energy, which is always for example, the entropy is always linear in the temperature. There is the part of the 4-point function that comes from the explicit conformal breaking, and that part leads to a chaos-like behavior with maximal growth in the commutator. That's common in both cases. That's what we discussed already. And also, there was a recent paper by Gao, Jeffries, and Wall, which shows that wormholes can be made traversable when you add double trace interactions, when you mix the two sides. And again, those effects can be, so you can add again some interaction between the two sides of the thermophile double. And the fact that the wormhole becomes traversable is again a simple consequence of this Schwarzian action that we discussed. So all these effects are consequences of the simple Schwarzian action. So in other words, the Schwarzian action captures all the effects of gravity in two dimensions. So so both this chaos-like growth or traversability of wormholes and so on. So all the effects that have to do with shock waves and the time advances and delays that you have when you have shock waves are captured properly by this Schwarzian action. What? I'm done. Yeah. So we go back to his paper, and I think, again, all these properties, in the words of Nati, they cyber-excise the problem. Thank you.
Thank you very much. Any questions?
Does your Schwarzian effective action play a role in the computations of AdS2 path integrals done by Ashok and collaborators?
No.
Why not?
So those are computations done of the extremal entropy. And so normally they really throw away all this Schwarzian action piece. So the Schwarzian action involves some deviation away from AdS2, and they are really throwing this away.
But if I take this,
and so they determine the near extremal entropy, but never the extremal entropy. So the Schwarzian action is irrelevant, is not important for the extremal entropy, and all those works are related. So the talk of Murthy we just heard involves the extremal entropy.
But what confuses me is that the contribution that you were talking about seems to go to infinity, not to zero when you take
Yeah. But I haven't fully understood, but I asked this to Ashok explicitly, and he says that, well, this is just some factor, it's infinity, but you throw it away.
I have a bunch of questions. The Schwarzian, is it exactly the same as the 4 fermions, or can we just forget about the 4 fermions and discuss just the Schwarzian Lagrange?
No. So the 4 fermions are the same as, the Schwarzian is like a piece of so the 4 fermions are like a whole set of operators, or if you wish, fields that propagate in AdS. So there are a bunch of massive fields and this degree of freedom that has to do with the Schwarzian. They contains all these degrees of freedom. It's in some circumstances that you, So if you consider the correlation function, the Schwarzian gives the largest piece of the 4-point functions, the numerically biggest piece, right? But with a very specific time dependence. But if you look in more detail at the time dependence, you can read off some lower order pieces in the 1/beta J expansion that have to do with all the massive fields that the 2 fermions contain.
The second question is related also to a comment that David made yesterday, comparing this model with the C=1 model.
Yes.
There it's integrable and here it's chaotic.
Yeah.
There it's linear dilettron and here it's
Yes.
Yes. And other than that, are there any similarity, like the quote-unquote fields that propagate in the bulk, are they similar? Like, is there a tachyon field?
Yeah, no, I think it's different. So those C=1 models are a little more similar to the first model I discussed, where there is just the free fermions. And yeah, it looks really different. So in the C=1, there was only one physical field that was propagating. Here, there is a large number of, naively, there is a large number. Another feature is that the C=1 model, perhaps more important feature, is that it's a kind of standard large n limit, large n like matrix limit, where the number of fields in the bulk is independent of n, right? While here, you have these fermions, and these fermions look like things that could be propagating in the bulk, and there are n of them. at least in the simplest version of the model. You could imagine gauging and changing the model a little bit, but still you have more fields propagating in the bulk. So this model doesn't have a clear bulk, so does not have a known bulk description. So what I discussed here are some features that are in common in SYK and AdS2, right? Standard AdS2, nearly AdS2 spaces. So they have some common sector, but
there is some contradiction between this model having this infinite dimensional symmetry, almost integrable, probably in this limit, yet it's maximally chaotic. Can you comment on that?
Well, it's a good question. I mean, but this is a question somehow which is the same as saying that there is a contradiction between, gravity, which is simple, and field theory, and the idea that the same process in gravity can be reinterpreted as chaos in the field theory, right? So because let's just this 4-point function that we are discussing, that we discussed here, in the bulk, when in cases where you can calculate it using the bulk, corresponds to a 4-point scattering amplitude in the bulk that you can compute using standard gravity, which is weakly coupled and so on. And this chaos is related to the growth with energy of these correlators. And so here again, the growth is related to the chaos is related to the behavior of this system at long times, right? What it is doing at long times, and there is an exponential growth at long times. Now you can ask, why is there an exponential growth at long times? And it has to do with the higher derivative nature of this action. So this action contains some pieces that grow exponentially. Those are like zero modes that come from the action of SL2, right? Which if you quotient by the SL2, you remove them. But the problem is that in the out-of-time order correlator, you really excite these modes, and it's through and by exciting these modes, you got this growth in time. So in the out-of-time order configuration, those modes become physically excitable and lead to these effects. But I think it's a good question. We probably need to understand it better.